Wednesday. So the midterm is going to be a week from now, basically, from today. So midterm 1 is Wednesday of next week from 6:30 to 8 p.m. If you have a conflict with the midterm, then you have to send us email. You have to do it by the end of today. If you have a conflict, then there's an alternative time where you can write the midterm. Additionally, there's going to be an embargo on the Piazza and QA overall. And that will start Tuesday at midnight, and it'll go until the midterm. And finally, we will be posting a sample midterm, either today or tomorrow. But the midterm is going to be a little bit different. So don't expect the midterm to be identical, but it's a good way of studying for the midterm. In terms of the things you should be worrying besides the midterm. Yeah, programming assignment number 4. Due Sunday night. You're working on lab 4. You have exercises and meetings. So, I mean, I tell this to everyone. If you really want to prepare for the midterm, you should be doing the exercises that are posted. So the exercises are really the best way of preparing for the midterm. And then the schedule will basically be, on Friday we're going to do a lecture lab here. And it's going to be for all the topics that was covered so far. So today is going to be the last day of covering topics for the midterm. Then Monday there's going to be a QA. There's going to be a review. If you ask me questions, we're going to go over the material. And then Wednesday we're going to go over programming assignments. So I know that we haven't really, you've been solving them on your own, but we haven't been going over them. We haven't been giving you solutions. So we'll cover some of the solutions to the programming assignments that you've been working on. Including programming assignment number 4 that you're working on now. So that's the schedule for this action path. This next week is action path. Just to review where we were last time, and then what we're going to cover today. So here's kind of the outline for this section of the course. And we talked a lot about type hierarchies, right? Subtypes and supertypes, and what it means to be a subtype, and when is it legal, to make a type conversion between one and the other. We also talked a lot about inheritance, which is a way of cutting down on code duplication. So this is the case where you have a superclass, and you're going to create subclasses, and the subclasses are going to retain all of the behavior of the superclasses, and modify only the behavior that they need to locally. And then at runtime, how does Java know which method to invoke? So this is where you have a parent versus actual type. And this is the process of declaring this method. And then finally, overriding provides you a means of declaring methods that have the same names, but may have different arguments. So today, we're going to talk about type-substitutability and compatibility. It's a more confusing topic, and it's the grand finale. So in order to understand type substitutability, substitution, you have to really kind of know and understand all of the above. So this is really the culmination of this topic. But what I do first actually talk about why we need it. So this came up on Piazza, actually, about, so we're defining these multiple levels of abstraction. We're defining interfaces, we're defining abstract classes. And the question is, why do we need these things? Right? Because you can always do without an interface. You can sort of flatten your hierarchy, your type hierarchy, and eliminate an interface if you wanted to. So what do you gain by having an interface? So the example is the following. Let's say you're a phone manufacturer. Right, so this could be an Android phone, this could be an Apple phone, and until recently, phones were basically just very customized hardware, and the software was highly customized as well. Right, so there was very few things you could actually execute on a phone until very recently. So now what you have are these things, which are apps. So everyone that has a smartphone has a bunch of apps installed on their phone. So as a manufacturer, you don't constrain the kinds of apps people can create, right? Because you want a lot of diversity. So if you're a phone manufacturer, you basically take care of the hardware, and then you have some developers here on the side, all these people. This is the best I can do. And these guys, in garages, in office spaces, in schools, are going to take care of implementing these apps. Right, so every one of these apps was designed, implemented, and then somehow distributed to the consumers through some process. And all of them seem to work seamlessly on your phone. Well, sometimes they crash, but mostly they seem to work, right? So the question is, how does this happen? This seems like a really complex ecosystem. You allow anyone in the world to write code, and then that code is supposed to execute on your computer or your phone, and it's supposed to just work. Right? How do you make that happen? It's crazy. So interfaces is really the answer to how this works. Because really the way to think about it is that here there's a boundary. And this boundary is sort of a boundary of abstraction. Right? So when these developers write software for the phone, they're writing it against this abstraction, against this interface, which presents an abstract. So for example, when you get a new version of the iPhone or a new Nexus, your apps will still work on that new version of the phone, so they don't care about the kind of hardware that you execute, more or less. Really what they care about is this interface, this abstract phone representation that you encode with your interface. Right, so from a developer perspective, your phone looks like, there's some operating system, and then there's some hardware here. Of course, as a developer, I really don't want to care about the hardware. And up top, you have these apps. And all of these apps are nicely isolated, so they don't depend on each other, right? You don't want them to step on each other's toes. And you have many and many of them, and they all talk to the operating system. And the way this happens is that the operating system, if you really wanted to look inside of it, it has a bunch of interfaces. So an operating system takes care of managing the hardware, but it also presents an abstraction to the software. So you might have an interface for example, the screen. Right? And the screen might have the screen interface. The screen interface might have a few methods like tap, or maybe drag. There would be some integer start position, and some integer stop position. So you'll have a bunch of these methods defined in an interface, and then an application is some piece of code that implements that interface. Basically says what happens when you tap on a screen, what happens when you drag on a screen. Right? The operating system doesn't want to define that because the operating system wants to let you, the developer, design the application. So it gets out of the way, but in order for all of these apps to coexist, they all need to follow a common interface. Right? So this is a really good example for why interfaces matter. Because in the real world, you often don't know who's going to be writing software for your phone, or for your operating system, or for your web server, or whatever. So, interfaces is a way of getting you this variety under some constraints, right? So they constrain the kind of, what does it mean to be a screen? But it's constrained in a very abstract way. That's why we need interfaces. Any questions about this example or interfaces?
Where do the developers get the interface?
Where do they get it? Well, they go to Apple's webpage and they download the specification, right? Or they run Xcode, or they run Eclipse, and they download the Android SDK, the development kit. And basically, part of that distribution is a set of interfaces. So yeah, so somehow the manufacturer has to tell these people that, my interface is the following dash line. And this dash line will vary, right, between different phones and so forth. And the quest is really to make this dash line as similar to other dash lines as possible, because that'll make it very easy for your app to work across different devices. So that's interfaces. Okay. So let's get to type substitution. So the context for type substitution is really one of semantics of a statement in a programming language. So let's take a look at a very simple example of syntax versus semantics. So a really good example is just the English language. So when I say something in English, all of you speak English, so all of you understand what I say. And so I may say something like, she is a swimmer. So this sentence is grammatically valid, and it has clear semantics. I can also equally say something like, he is a swimmer. Also legal, right? Semantically, it has the syntax checks because, I have some pronoun, I have some verb. So the construction of the sentence is legal. And then semantically, it's also valid. But if I write something like, she is pregnant, then I can't really substitute he, she for he, right? If I write he is pregnant. So this is still a legal sentence, right? I can still say it, and it can be parsed. So syntactically, this is okay. But semantically, it's really bizarre, right? Because semantically, you reason about the world and you say, how can he be pregnant? It's not possible, right? So this is English. Now, for programming languages like Java, you have a very similar distinction between syntax and semantics. So in Java, typically the way we think about syntax and semantics is in terms of statements, right? So a statement in a programming language is like a sentence in English. And some of these checks for syntax and semantics can be automated and some cannot. So for example, I can define a variable I, int I, and that's legal. And then I can do something like I equals 5. And that's okay. It has a semicolon, right? I have the variable I, it's declared as an integer. And the reason this thing is semantically valid is because this I, the type of this I, type is int. Whereas the type of this 5, type is also int. So this is why the statement is actually legal. Right? This is why I can do this. So syntactically, it's very easy to check that a statement is legal. Semantically, it requires a little bit more knowledge. You have to actually know what 5 represents. And you have to know what I represents. So this is a very simple one to check. But what if I had I equals I plus 1? Then you have to do a little bit more reasoning. You have to say something like, okay, 1 is an integer. I is an integer. This plus expression takes two integers and produces an integer. And this thing on their left is also an integer. Okay, great. Thanks. So what I'm doing here is basically checking the types of my expressions and then making sure that they're compatible to make the assignment. So when I do something like I equals 5.5, the same thought process will lead us to conclude that this is a problem, right? Because this thing is not an integer. This is type double. And this guy is still an integer. There we go. Hopefully it'll stay like that. So this is illegal, right? I can't do this. Type I equals 5.5 is illegal because I can't assign a double to an integer. So this is really simple for primitive types. So I is a primitive type, 5.5 is a primitive type. Now I have to, in the context of what we talked about, if you have a type hierarchy, you're adding new types to your language. So you have to be able to reason about, compatibility between types that you've created yourself, that you've defined. So that becomes more tricky. So this is like primitive types. And this is user defined. Or really just anything complex. Like instances of classes, objects. So you might have, let's go along this example of the mobile phone. You might have a class called app, and then I'll have a little class hierarchy where I'll say that app is actually subclassed by maybe a Facebook app. Maybe PayPal. We'll have this little type hierarchy, and now I can reason through the same set of things, right? I can reason about compatibility between my types. So I can say something like app A, and I define an app. And then I can do A equals new FD app. So why is this statement legal? It's not like the example above, right? Here I'm just saying, okay, the thing on the right, expression on the right evaluates to int. Expression on the left is an int. So it's legal to assign one to the other. But here, my FD app, it's a different kind of thing, right? It's a different type of thing.
FB is subtype. FBF.
Right. So the key thing is this relationship. Is the subtype relationship. So my app, this app thing, is a superclass. Really, I should be saying supertype. And every app is a subtype. So it's legal to assign an instance of a subtype to a supertype. And we talked about this before, right, with different credit cards. So this is kind of, we're just extending what it means to do a semantic check in Java to more complex objects, to objects that have hierarchies and have these strange relationships between them. What about this guy? So what if I defined a new variable and I had something like then I did S equals new app B app. Would that be legal? Why not? Yeah, they don't belong to each other, or really a better way of saying that is that one is not a subtype of the other. Right? So there really is no relationship between these. But I could do A equals S, right? If I didn't have the statement. A being the app. Right, because still, this is still a subtype. And this is still a supertype. So it's still legal. Okay, what if I extended this thing? So what if I had Skype app, and then I subclassed it. I created a new kind of application that provided premium service. So I'd have a premium Skype app. So my type hierarchy got more complex all of a sudden. And now I want to say something like Skype app equals new premium Skype app. Is this okay? It is, right? Because we have a similar relationship, right? I just built it a little bit. I just built the type hierarchy a little bit deeper. So this is still the supertype. And this is still the subtype.
In your first constructor, do you need the two parentheses or can you do it like that?
Yeah, I'm actually attempting to build objects, so that's a mistake. Yeah, I'm actually creating things, right? So the new keyword wants to call a constructor. It's a method call, so it needs to have parentheses.
So in the first example, can we change the app A to the page equals app and then A equals new app correct? So we switch the page equals app and the app. Is that correct?
Well, yeah. If I did something like, let's say FB app, and then I said new app. Is that what you meant?
Yeah.
Is that legal? What do you guys think? So who's the supertype and who's the subtype here? There's obviously a relationship between them, right? So this is the super, the sub. So, not allowed to do that, right?
Was an app an interface anyways?
Is the app an interface? Well, how do we represent interfaces?
Dotted line.
That could be a dotted line. I can't subclass an interface, right? So this is the extends relationship. It's not an implements relationship.
There's no arrow from premium Skype app because there's no subclass and superclass relationship.
Yeah, it's mostly just my mistake. There should be an error.
So you could have app S is equal to new premium Skype app.
So I could have app,
S is equal to new premium Skype app.
the premium Skype app. Yes. You can, because this is super. And this is sub. Right?
How many levels there?
It doesn't matter how many levels there are. That's right. So this could keep, it could be extending FB app as many times as I want.
When would you want to call the bottom one versus top one? So app-ass versus Skype app-ass.
When do I want to do this versus this? Yeah, it's a good question. It's a question of abstraction. So when I declare S to be an app instead of a Skype app, then the way I think about S is as an application. I know less about it. It's more abstract. So for example, in my operating system, I might have a statement like this, like app A equals new app. And it doesn't really care what kind of app it is. Okay, it doesn't care that it's Skype Premium app or this FB app. All it knows is that the app is on the screen, and I can tap on it, and I can drag on it, and so forth. But if I'm actually inside the app, right, inside of Skype, then I might actually want to declare this. Make S a premium Skype app or a Skype app. So it depends on where you're using S and what you're using it for. Right, so this is more abstract. This is useful for like an operating system that needs to know fewer things about the details of the app. Great. Other questions? This thing keeps going to sleep. I don't want this out. Okay. All right. So this is mostly a review right now. Let's get more interesting. Now let's get to actual substitutability. And the key to substitutability is this principle, the LSD principle, which is the Liskov substitutability principle. And it has two parts. And so I'm going to give you an example of each of the parts, and then I'll kind of bring them together. And for that, we're actually going to look at the credit card example again. It's the easiest one to look at. The reason we need to look at actual code, as opposed to kind of our little diagrams here, is because we need code with some specification. So let's look at this credit card interface again. This interface defines these two methods. I can authorize some amount, and then I can complete a payment. So this authorized amount has this specification at the top. And the specification tells me that the input to authorize amount, this amount variable, must be greater than 0. So that's a requirement. So that means if you call this method, the value that you must provide must be greater than 0 in order for you to get the effects that you want. And if you don't give me that value, you can't guarantee what the method will do. Right? So this is, you can assume as a programmer that you will get this as long as you satisfy this. So typically the way we think about these is in terms of preconditions and postconditions. So a precondition is something that must be true before you execute something. So in this case, this is the requires clause. And a postcondition tells us what is true after you execute some code. And this is basically our effects clause. So substitutability is a way of reasoning about compatibility between preconditions and postconditions within the type hierarchy. And this reasoning is kind of deep. So to illustrate this, we draw this type hierarchy for credit card again for this project. So remember at the top, we have the credit card interface. And then we implemented this interface with two cards. We had the ASIP card and also the subordinate card. Let's say that hypothetically, I want to add a new kind of card. And I want to add a card that's going to be the premium card. You know, like premium card. And this premium card has this interesting feature that in order to use this card, you need to use it when your purchase is large enough. You can only use it on really expensive purchases. That's what makes it premium. All right, so we can look at the preconditions for the credit card interface for the authorized amount. You have a statement like this, and the requirement is that amount is greater than 0. Now in my premium card, I'll have a very similar method, but I need it to behave slightly differently. I need it to have a different specification. So I'm going to override it. Sorry, overload it. And give it a requirement that amount must be greater than 1,000. So the signature for my method is identical. Just takes some double value. So now I have two specifications for types that are related, right? I have credit card, which is an interface, and it's my super type. And then I have the premium card, which is a subtype. And I gave you two specifications for the same method, the authorized amount. So let's reason about what happens if I write some code that attempts to use this method. So I could write some code that says credit card C, find a credit card, and I could say C equals new ASIP card. Then I can actually do C.authorize amount. I can give it some number. 5.0. So this code creates a new instance of ASIP card, assigns it to C, which is a super type of ASIP card, which is a legal assignment, and then it calls this authorized amount. And this 5.0 satisfies this precondition for authorized amount defined in the interface. So let's contrast this with the case where I attempt to create a premium card and use this interface. So I'll do C equals new premium card. And I can call the same authorized amount on it. The same value. So what's the problem with this last bit of code that I wrote? Barely see the whole thing.
Numbers that are greater than 1,000.
That's right. So my precondition for the premium card, my requirement is that amount is greater or equal to 1,000. But the value I'm passing in is 5.0. So, okay, so that looks like I'm violating the precondition on the actual type of C, the premium card. But C's parent type is credit card. So if you look at the parent type of C, and if you look at its specification, right, it's right here in the code. It says amount has to be greater than 0. I didn't violate anything. And it seems like a problem, right? Because C, this type that I'm using here, has a specification. And then what I've done is I set it to this actual type premium card. And in a sense, this is where substitution comes in, right? I'm talking about C, and I'm treating it as a credit card, but the actual type is a premium card. It's actually a different thing. And now the question is, when is it legal to treat it as a premium card? When is it legal to say C equals new premium card? And this is one of the cases when it is illegal to treat C as a premium card because there's a problem between these two specifications. Because this precondition is stronger than the precondition of the supertype. So this is a huge problem. So you're not allowed to define a precondition that's going to strengthen the precondition of a supertype. Okay? And that's half of the LSD principle. Basically says that when you have this type hierarchy, in order to semantically reason through this sort of code, I have to think about the specifications, and I have to think about the preconditions and the postconditions of the methods for all of those types. And so when I have a specification that looks like this, it's a problem, because I can't substitute premium card for card. I can't think of this as a card, because according to C, the parent type, it is legal to do this. But for my premium card, it is not. Okay? So this is the problem with the precondition, where the precondition that I gave you is stronger than the precondition for the supertype. So condition, so rule number one, I can't spell rule. Rule number one must have same or weaker precondition. And this applies to on methods of a subtype. So what do you think I mean by weak or stronger? What is this terminology? Why is greater than 1,000 stronger than greater than 0?
Because greater than 1,000 implies greater than 0.
Yeah, that's one way to think of it. That's a really good way. So basically it says that this statement implies this statement. And it means it's stronger. Another way of thinking about it is that if you consider the values of amount, the set of values that are constrained, or the set of values that are defined by this precondition, is smaller than the set of values that are defined by the precondition amount greater than 0. Okay. So it's stronger. This guy is stronger because it constrains the method to fewer things. It constrains the kind of amounts that are legal. So that's what I mean by stronger precondition. So it would be legal to have a different precondition, which is something like amount greater or equal to negative 1,000. So that would be okay, because I weakened the precondition. I allowed more values. Okay, great. So let's talk about the second half of the rule. And the second half of the rule has to do with postconditions. So this is rule number 1 of 2. So when we write code, we have to reason not only about the precondition, but also the postcondition. the post condition is the effects clause in our specification. So, a simple way of demonstrating this is perhaps with a new kind of method. So let's say I wanted to add a new method to my credit card. And I wanted it to be something like public double balance owing. So let's say I want to just check what is the balance on my card. How much are you owed your credit card company? And so the requirement for this, well, it's nothing. You can call it whenever you want. Right? There's no constraint on when you can call balance owing. It doesn't modify anything. So modifies says that it says nothing. But the effect is going to say something like, returns the amount owed to the credit card, to be on the credit card. Returns an amount greater than 0. Amount owed on the credit card. So that would be my effects clause for this new method in my credit card interface. And so what I just said is that balance owing, doesn't require anything. So it always returns some amount that is greater than 0. But if I look at the platinum card, and I wanted to define this method. So let's say I also want to say double owing. Doesn't take anything. But the post condition I want on my platinum card, because it is so special, this card, I want to return amount owed I want this amount to be greater than -1,000. So you could have credit on your credit card, right? Could be that maybe they gave you back some money, some cash back, and the amount owed is actually negative. So this could be a potential post condition, or this effects is a post condition on this method, the amount owed. So now we've come up with this scenario. Now let's see what might be a potential problem in the post condition sense of substitutability. So again, I'm going to define credit card. Credit card C. And I'll say double D. Say equals new platinum card. And then I'll say C dot D card double D equals D dot amount owed. So here's my code. So what do we expect D to be? At the very bottom I say double D equals C dot amount owing. My post condition for credit card says that, D must be greater than 0. Right, that's what this thing says. Well, my post condition for the platinum card says that D must be greater than 1,000, negative 1,000. That's this thing here. So again, there's a problem, right? Because after I derive this value, I'm going to go on to do something with this D. Right? I might add it to some number, I might use it for accounting, and I need strict guarantees about what D is, what kind of values it may have. So according to one specification, D is greater than 0. According to another one, it's greater than 1,000, negative 1,000. And that's an issue because this is a weakening of a quotient. And it's a problem because when I get this D back, I'm treating C as a credit card, and what I really want to make sure that D is greater than 0. But I can't guarantee that with this new specification for amount owing on the platinum card. Because now my D can be negative. Right? So this leads us to rule number 2 of substitutability. Says that methods of a subtype must have same or stronger post condition. Right? So it has two parts to it. The first one says that the precondition, if you have a subtype and defines a method that's also in my supertype, then I must either keep the same precondition, or I could weaken it, and I must keep the same postcondition, or I must strengthen it. So that's what substitutability is about. So when we get this code like this, my compiler is not going to tell me that this is illegal, right? Because it can't do these sorts of checks. Because you have to reason about my specifications. And my specifications right now are in the comments. So you can't really make this check for me. So you, as the programmer, have to make this check. Questions? We're out of time, but we're going to review a lot of this on Monday, and then Friday is going to be lecture lab, where we're going to practice something.